So I guess I can apologize to those who are remote. All 0 of you live, but all of you looking back that I didn't have the ability to record yesterday. Power was cycled in the building and the IT person was unaware of this. So just about all of the recording capabilities in classrooms were broken. We're back at the lab today. It was probably the wrong day to miss though. So we're gonna go over a little bit of what we did last time and then augment it with an example, because as with anything this complicated, it's very important to have an example. So we are answering the membership question. I guess we should probably go back one more and introduce the Is the query string in the language defined by the grammar? The assumption that we need to make is that the grammar is in CNF, because then we can apply CYK to it. We're gonna break down the string down into its individual characters, C1 through CL. Those are the characters that are in the string. L is the length of the string. And we will say as well that Wij represents the substring from the ith character up to and including the j character. This is because we are 1 indexing this rather than 0 indexing this. So the first character is C sub 1, not C sub 0. And this is C sub L, not C sub L minus 1. So I is the initial index and j is up to and including the last index. So W13 would be C1, C2, C3. Then we said we're going to define n sub ij as the subset of all, I guess, productions. The non-terminals that are on the left-hand side of a production that can produce this substring through some sequence of productions. And we'll see exactly what this means, I think, with a better example here momentarily. But this basically means that if this were the start state of some grammar, starting here, we could find this substring via some search through the legal production forms from here. As we do all of this, the goal, the question to answer is that can the start state of this grammar generate n1, and I really think it should be L here, not n, but I just said that L of G is the language of the grammar, but we want to go from 1 up to the length of the string. Man, this is shocking this morning. Shocked myself twice. But we want to go from the first character all the way to the last character. If the start non-terminal via some sequence of productions can produce this string, then this string is in the language that's defined by the grammar. So the process we're going to go through for this is to use a dynamic programming algorithm, CYK. We're going to start with the easiest questions, and then we're going to use the answers to those easiest questions to build up and eventually reach this answer, whether the start non-terminal is in this capital N sub 1, capital L, or capital N sub 1, and whatever you use, just make sure it's consistent. So we're going to start with this first step. Compute all possible n sub I, which is n sub 1, n sub 2, all the way up to n sub capital L. That tells us whether we can generate substrings of length 1 with any of these productions. Then we're going to go through everything n sub ij where the difference is 1. So we'll do n sub 1, 2, n sub 2, 3, all substrings of length 2 within this string. And then we're going to find all substrings of length 3, and we do this until there's just the one question, substring of length, the length of the string. So we're going to go through this in arduous detail because this is going to be your big lab for the quarter is implementing this algorithm. In fact, I can probably reveal that assignment later today, even after this example. And it won't be due till the end of the quarter. You'll have the rest of the quarter to work on it, but I wanted to get you started on it as soon as possible so that you can start, get stuck, iterate on it, come get some help, and that way, but it's not a crunch at the end of the quarter. I say that and I fully expect about 80% of you to be crunching at the end of the quarter with it anyway, but here we are. All right, the string we're going to be looking for is AABEB, and the CNF grammar that we're going to use is here on the board. So we can see that all non-terminals either lead to two non-terminals or a single terminal. And we're going to proceed because I don't think we really have enough information to have you do this yourself. I think we really need to go through this in the class. So let's see, where do I want to draw this? Do is know the size of this so that I can kind of draw it down in a corner. Because we're eventually going to be revealing some stuff. But so we're going to have a, let's see if that's enough space. First row is going to come all the way out to the end. Second row all the way up there. 3, 4, and 5. That's pretty good. My second grade artistic abilities are coming in clutch here. All right, there's a stepwise. This is kind of the chart that we're going to be filling out. The length and height of this are going to be equal to the length of the string that we are trying to query or find, whether it's in the grammar. We can see that this string is length 5. So this dynamic programming 2D array that we're going to make here is going to be length and height 5. So this first row is going to represent all capital N sub II, all substrings of length 1. This is going to ask the question, how do we produce which of these productions can produce the substring that is the first character of the query string here. So we can see that W11 is just the substring A. So capital N sub 11 is going to be the set of every non-terminal that can immediately derive that character. So we see that it's right here. Here we have a production that is capital A, arrow, lowercase a. And that's the only production that can derive that character. So what goes in this box is the set A. All non-terminals that can derive that substring. And again, this lower row is going to be easy. Everything else is going to be significantly harder. So now go ahead and fill out the rest of the row. What goes in the rest of this row?
The A of it would be B. It would have to be B, right?
Yeah. Yeah, so this box represents that substring, exactly this character, this A. So now we can ask the question exactly what subset of non-terminals derive that. It's exactly the same question as this. It's the same query. So this is also the set that contains the non-terminal A. The rest of this row is going to look the same as each other because we're looking to derive the same substring, B and B and B. And there's only one rule that can do that. It's capital B arrow lowercase b, so. The easy part stuff. Great. So now we're going to start moving on to using this information to construct the second row. Before I reveal the exact process, let's kind of ask the question and derive it. So first, what does this box here represent? What does this array index represent? So all of these are going to be sets. So it's the set of non-terminals that can derive the substring starting at 1 and going up to 2. So we want to figure out via what process can we derive AA. So to do this, we have to use the concept from the last class of we're going to split this substring into a left side and a right side. Each of those left side and right side have to have lengths of at least 1. So this row will only have one possible midpoint for that. We're going to take this AA. That's double quoted. And we're going to split it the only place we can. So we're going to call this the left-hand side. We're going to call this the right-hand side. And now the question is, do we have what can produce this left-hand side? Well, this left-hand side is this subproblem. Right? We're trying to figure out what produces the A. That A is exactly this character. This question was answered in this box. So the left-hand side can be produced by the non-terminal A. We're now going to ask exactly the same question with the right-hand side. What can produce the right-hand side? Well, this substring is from 2 to 2, which is this box. So this box also has a right-hand side of A. So in order to be able to produce this, there must be a rule in the grammar that says something arrow A. If that rule exists, then we can derive that substring. If that rule exists in multiple places, this set will contain multiple elements. If there is no such rule, and we can see in this case, there is no something arrow AA. You only get AB and BB as the possibilities for the non-terminals that we can produce. So because of that, this is the empty set. There is no such rule such that when we break this substring down into any possible left or right-hand side, we have a rule such that something arrow that left side, that right side. Question?
So. Okay, so you're just talking about the non-terminals.
Right.
Okay.
If this rule existed somewhere in one or more places, then this question mark, whatever that happened to be in this grammar, would be added to this set.
Does it not count that you just leave the first A alone and turn the B to AB?
We can't leave the A alone because there'd be no way to generate this substring.
Or not like leave it alone, but like just do S equals AB, then you go S equals AAB. Then change both A's.
That will show up here.
Okay.
As a possibility. We only care about deriving the AA for right now. Again, the third row will be any substring of length 3, which may use this as one of the possibilities, but there will be other possibilities of breaking it down such that it will be possible. That is a great point. And good job looking ahead and thinking about how we're going to be constructing this. But whenever there are options like this, we got to break them down into some kind of algorithmic process. Because computers aren't going to have that critical thinking and that ability to see ahead, that there is actually a way to do this kind of if you do this, because I will spoil this string is in this language. So even though we can't from this grammar directly make one of the substrings, That does not mean that no string with that substring exists in the grammar. We just can't derive a end of string. But we can derive strings of other types that involve that substring. Does that make sense exactly how we fill out this box? All right, so I'm gonna erase this and we're gonna kind of start over with the next box. So this box represents what substring? AB. AB. We're starting at 2 and going up to and including 3. So again, this represents N11, N22, N33, 4, and 5. It's very common to think that this is 1, 2, 1, 3, 1, 4, but that's not the case. This is 1, 2, this is 2, 3. All substrings of length 2. So if we're looking at lowercase a and lowercase b, we now want to take this string a, b, and break it down into its left side and its right side. Its left side, we've already calculated. Here are all the possibilities for that. So the left-hand side can be done with the production, the non-terminal A. The right-hand side can be done with the non-terminal B, which we grabbed from that box. So now we're looking for some rule, something arrow A, B. Does that exist in the grammar? Production S. Production X. So we want to add that to this set. What else?
Okay, do we have to have the brackets or can we just write under the letter, or are you gonna want us to write brackets?
It represents a set, so it's useful to write them as a set. You can, if it's better for your knowledge, or if you don't have the space for it easily, then I guess. But I guess the answer is technically no, because it's a set, we want to show it as a set. What other production can produce A, B? B. So there's nothing that says that this set has to be of size 1. It was down here, but there's nothing that says that that needs to be. These sets can be of any size really up to the number of productions that map to the non-terminal arrow, non-terminal, non-terminal. Because some grammars will have all of those being the same, but most won't. So this is what goes here. So now my question for everyone is to fill out these last couple of boxes. What goes here and here? Using this same idea. Fill out everything that's left of substrings of length 2. Also, I forgot about this, but I discovered how to make this HD yesterday. And I realized that I forgot to do that in here. So everything up until this point has been blurry and gross, and we now live in a world that is, what, 2004 or later? We lived sometime in the last 20 years. I don't know why the default would not be HD. What did we get?
I just got A and an A.
A and A? That is right. How do we get that? How do we know that? So for the following strings, we're gonna take BB. This is going to become the left side, that is B and B. We're gonna refer down to here and here and here and here now. These are the lookups. Figure that out. BB and BB. So the left-hand side is a B. The left-hand side of this question mark is a B. Where does BB show up? We have A arrow BB, so we add A to each of these. That is the only production that leads to this. All right. Now it's going to get even harder. I would say that the difficulty of this row is level 0. It's really easy. This one, it's like what, level 2? Not too bad. Now it's going to get worse and worse as we climb every single layer. It gets harder and harder. So what do we do to fill this box? What does this box represent? 1, 3. 1, 3. Absolutely. So 1, 3 is the substring AAB. So if we're going to bring this down now, we have AAB as the main string of focus. What is the left-hand side and the right-hand side of this? We have options. So we're going to start creating something like a little tree structure. That's at least how I like to think of it. You can split this up however you'd like, but on the left-hand side here, we're going to have a smaller left-hand side. So here we have a left-hand side of A and a right-hand side of AB. And now here we have a left-hand side of AA and a right-hand side of B. We need to consider all of these. There's no way around the optionality of breaking this down. So let's move down this case. Left-hand side of A, right-hand side of AB. Luckily, we have some lookups that we can help us do. This A represents what? What box that we have filled out is this substring? This comes from here, which comes from there. So it is capital N sub 1, 1, so the lookup comes from here. So we're going to take this as the left-hand side here. A is the left-hand side. What about this AB? Where does that AB come from?
S and B.
Yeah, we're looking at this box because this is N sub 2, 3. This is the substring from 2 up to and including 3. So what this tells you is this is, now I'm actually going to start drawing this as sets because it's easier to not think of them as sets at first, but you need to start thinking them as sets. If we're going to concatenate something from this set with something from this set, we end up with options. So the options here are AS and AB. Right, taking something from the left, concatenated with something from the right. Depending on the size of these, you get different numbers of possibilities. So what we're going to add to a large set of possibilities is we eventually want to find all such non-terminals that can generate any one of these breakdowns. And we have found that any production of the form question mark arrow AS and question mark arrow AB are capable of producing this particular breakdown. So is there anything in here of something arrow AS? No. Is there anything of the form something arrow AB?
Yes.
Yes. So S and B can both produce this. So we're going to add S and B. to this set. As the question marks that can produce this particular production in this grammar. However, we are only half done, because we now have to consider what happens in this case. So we're going to break this down, and this AA, where do we find that in the lookup table?
So can we, or is it the answer still no? This is because it was no earlier, so it's still no now.
Correct. Yeah, I think I see where you're going. The lookup is to this spot. To capital N sub 1, 2 is this substring, is the first couple characters of this string. So this lookup is going to point us here. So the left-hand side of this is the empty string. Now, if you're programming this algorithmically, we can kind of stop now. Because if what we're looking for at the end is something from the left-hand side concatenated with something from the right-hand side, we're not going to be able to create a legal production that is going to be in CNF. But for the sake of knowing where this comes from, this B is the third character, so it's going to point down to the first row right here, to this B. So we see that the right-hand side of this would be the set that contains B. And we cannot construct any production out of this, because this is empty. So this result is empty. There's no possible thing that we could do here, so there's nothing that we can add to this set. So it turns out that we're done. I left extra space here in case there happened to be something here, but there is not. If there were additional copies of things like S and B, since this is a set, we don't add extra copies to it.
So would we not always use the whole table? Or are we gonna just keep them filling it out?
We do have to keep filling it out, because when we break this down, one of the options is gonna include things from this row. One of the things is gonna include things from this row. So yeah, we have to, in order to answer this question, we have to have potential lookups to everything else in the table.
When you said that we were done, I was like, wait, really?
We're done with just this small subproblem. So this S and B is what's gonna get ported to this square. Great. All right, we're gonna start over. We're gonna do another subproblem. So now instead of AAB, we're gonna do the next substring of length 3. Which is ABB. So if we want to do this, we're gonna bring down ABB. And we're gonna make our little tree of what are the different ways that we can split this into a left-hand side and a right-hand side. We can have a left-hand side of A and a right-hand side of BB. We're gonna have a left-hand side of AB and a right-hand side of B. The two different ways to split this up. Such that the left-hand side and the right-hand side have at least one character in them. All right, the lookup for A. Now this is the second one, not the first one. So we're gonna come down here for our lookup in our table. And we're gonna see that A can produce that. So we are going to say that, I see I did this before. The left-hand side of this can be produced by A. The right-hand side, BB, is a lookup into N34, which is right there. One, two, two, three, three, four. So the right-hand side to this is also A, because that's what's in that box. The first one was that box, the second one was that box. Is there any production of type something arrow AA? Since that is the only option for grabbing something from the left-hand side and something from the right-hand side. We look back at our grammar, the answer is no. No such production exists with a right-hand side of capital A. So nothing comes from here. Nothing gets added to our large set of things that can produce this particular substring. But again, that's only half the problem. that considered one possible breakdown. Let's look at the other possible breakdown. So AB comes from there, 2, 3, which is here in our lookup table. This is n sub 1, 2, 2, 3. So the left-hand side to this is either S or B. And the right-hand side, B, was n sub 4, 4, which is right there. So the right-hand side is B. This gives us two possibilities for what we come from here. We have a question mark arrow SB or a question mark arrow BB. Any productions of either of those forms? Yeah, there is a production right there, A arrow BB. So we can add to our large set down here of all possibilities an A. And now that we are done with both of these, we can port this set over to this box. So this is just the set that contains A. All right, one more of these on row 3. Any questions on anything we've done so far? How we've generated any answers in any of these boxes? Yeah,
So, what are our questions for the next part?
yeah,
So at this point, if you still have everything written down, can you just be like, okay, if we have B and BB, we know over here that equals this, so just plug that in. Can we start just plugging things in at this point?
it's not easily. Unfortunately, there are. Yeah, the actual calculation needs to be done. What you will know is what the subset of boxes you need to look at are. That's what you could generalize here. Yeah, so like for instance, when we're trying to fill this box, the questions that we asked for this was the possible breakdowns were this and this. That wasn't that, it was this is 2 and 3, so it was this and that. That generated the AA. And the SB and B came from here and here. So someone, I'm not going to do this immediately, but if you were thinking about how do I program this, you could start to think about what are the rules that govern what lookup boxes we have here. I'm drawing this out longhand so that you get an intuition of exactly what work is being done underneath the hood. When you go to program this, look for patterns. Look for something that would say, what boxes do we look at in general to fill out a particular box? You can make your work a little bit easier by finding those patterns.
So like for B, or not B, but for the next one, it's like, it's just BBB.
Yeah,
You split it into 1 B and 2 B's and then 2 and then 1. Since we know that B is equal to B, we just do like B, and then BB, we know from earlier as well, is just A. So we just go just like, then we just immediately just go BA.
you could.
But then from there, you go like BA is not there.
Yes.
So cross
Yeah. So as usual in any algorithmic process, you can start taking shortcuts. As the professor, I try not to do that because if I do that, then it forces everyone to know the logical leap that I am making, which requires you to be where you are right now. So I'm gonna go through it longhand, but it's a good idea to start thinking about, can I make an intuition here? I would hesitate though to jump too much too fast. Because if you do this, you might be making an assumption about how something works. And if you do it out longhand enough times to make sure that that assumption is valid, then you won't end up making mistakes on something like a homework where you're asked to do this, or an algorithm where you're asked to implement this. I am the same way. The biggest knock that I could have on myself as an undergraduate is that I took pride in how quickly I could solve problems, and so I tried to optimize for that, and I ended up making a lot of mistakes because yes, I solved it faster than anybody else, but I hadn't thought through it at the level that I needed to in order to make sure that my thought process was correct. And I find that that thought process is common among computer scientists. So if that's something that's happened to you before, you're not alone. It's common. All right, last one, last box. Let's go through it in a bit more longhand. So we're going to have the string BBB. So we're going to break down BBB, and we can break this down into two segments, B and BB, or BB and B. Enough B's to make us all be crazy. All right, so lookups in the table. Left-hand side is B, that is 3, 3, that's coming from here. The right side is 4, 5, so that's coming from here. So the left-hand side for this is going to be B, and the right-hand side is going to be A. Coming from here, and coming from here. Left-hand side, right-hand side. Anything BA in the grammar? No. No question mark, arrow, BA anywhere in the grammar, so there's nothing for us to add to this set. On this side, BB comes from here, this A. The last B comes from here. So we have AB. Any ABs? Yes. We have S arrow AB, and we have B arrow AB. So we're going to add these guys to the set. That's what gets ported over to here. Questions on anything so far? Anything I can help make more intuitive, explain in a different way? All right, let's level up the difficulty and do this again. What substring comes here? Are we representing with that? AABB. AABB. Be correct. So we have A, B. I'm gonna leave myself a little bit of room because what's the branching factor of this associated tree? How many possible middle points are there? Three possible middle points. So we're going to make a tree with a branching factor of 3. Here, the left-hand side is A, and the right-hand side is ABB. Here, the left-hand side is AA, and the right-hand side is BB. And here, the left-hand side is AAB, and the right-hand side is B. And these all come from this substring. So when we have a left-hand side of A, let's look up to here, 1, 1. So this left-hand side, draw this down here again, is A. ABB is 2 to 4. So it's going to come from somewhere in here. The 2 tells you its index. So that's this one. We have an A on the right-hand side. Any production, AA? Something question mark AA in the grammar? No. This was a dead end. AA and BB are both of length 2, so we're going to have lookups into this row. So what do we have here? We have AA coming from 1, 2, which is right here, and we can kind of stop early here if we'd like to. The left-hand side is empty, so we're not going to be able to produce anything in CNF. The right-hand side of BB comes from 3, 4, which is right there. It's an A. It's also empty. This is starting to look bad. Let's see if this can save us. AAB is the first one from length 3, S and B. And the right hand side B comes from 4, 4, which is down there. Combining this, we can either get SB or BB. So something arrow SB or something arrow BB. Any of those exist? Yes. We have A arrow BB, which we've seen a few times as we've constructed this. So to our set down here that we're eventually going to port, we just have A. And that's what goes here. One more in this row before we're ready to do the final one with a final answer. Questions on anything we iterated here? People are still writing, so I apologize. Don't want to erase it while you're still writing. All right. Last one for this row. Thankfully, it's smaller. We're now going to move these to here. A, B, B, B. We're going to bring that down. Anything of length 4 is going to have 3 possibilities. We have a left side of A, a right side of B, 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 a left side of A, B, and a right side of B, B, and a left side of A, B, B, and a right side of B. Okay. This A is now coming from position 2 in the string. We're going to make a lookup down here to N22. That is a left-hand side of A. And a right-hand side, whatever can produce BBB, which is the last triple in row 3, which is S and B. So possibilities here are something arrow AS and something arrow AB. AB appears the same 2 places that it's always appeared for this. So we're going to add S and B to our end result. AB and BB, this is the second and last elements of this row. So we have SB and A. So here we have SB as the left-hand side and A as the right-hand side. Gives us options for question mark arrow SA and question mark arrow BA. Any such productions? There's no SA and there's no BA. So nothing gets added to this. Here, ABB is coming from the second in the 3s. So A right here, that's our left-hand side. Our right-hand side is the very last character in the string, which is right there. So the only thing that can be valid here is some question mark arrow AB, which we've already added to the set over here. And because it's a set, we don't add duplicate copies. We're only looking for some such production that can produce this. And it turns out that there are 2 ways to do it. This is the first time you've seen that here. This just says that if we break it down into this, we can go one way. And if we break it down into this, we can go another way. There are 2 different branches through the grammar that produce this substring. That's fine. We just care about, does there exist a cow, not how many are there. So now that we're done, we're gonna port this set over to this box. And we have one last question to ask, and I think we can do it with the remaining couple minutes of class. I know that we've done a very one-dimensional class, but because this is a project, I felt like it was actually worth drawing this out and going through this in this much detail because it's useful.
It's gonna be on your next exam.
Probably,
Is it gonna be this big?
maybe. So I can give you a little bit of an insight into my process. With 2 minutes left, I want to answer this question with a little bit of time for those who don't have to run off. I can explain my process. All right, so last thing we're considering is the entire string. We're finally getting to the question that we actually wanted to answer from the beginning. Can this grammar generate this entire string? But to answer this, we need a new tree with a new branching factor. What is that branching factor? How many possible middle points are there? 4. Man, this is annoying. Good thing we have computers to do this for us. All right, so a left-hand side of A and a right-hand side of A, B, B, B. A left-hand side of A, and a right-hand side of B, B, B. A left-hand side of A, B, and a right-hand side of B, B. A left-hand side of A, B, B, and a right-hand side of B. All right, those are all the possible midpoints. But luckily, we have lookups for all of these, as long as we can identify which strings they are. This A comes from right there. The left-hand side is A. Right-hand side is A, B, 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 which is the second one of row 4, which is right there. S and B. Great. Any ASs or ABs?
Yes.
ABs, yes, we can actually stop here. Because we have something to add, and it's the S. This AB, this S arrow AB, that can produce here, this AB, is going to add S to this set, which is the entire question we were trying to answer. Is S in the set that goes in this box? That's the only thing we care about. We don't care if there's any other production here. If this set were AB, we would reject, saying that there's no way that this grammar can generate this string. The only way that it could be generated is if we start at the start state and can generate this string. But luckily, this first path added S to that set, so we can stop early. If we wanted to go through the rest of this process, we easily could, but they're just lookups in the table in the same way that we did. Does that make sense? That's another common mistake I see with CYK, is people want to say, is this not empty? And that does not matter. The only thing that matters is S in the set that goes in this box? And the full answer is going to be yes, S and B go there. And we can add it right now. Both S and B would have gone in from this. But then the rest of this does nothing to add to that. So that would be what goes in the final box.
So once you're looking at the whole string, once you derive an S, that's really all you need to prove the thing.
Yeah.
When you want us to draw that, though, do you want us to include all of the possibilities in that top box?
It depends on what the question is asking. If the question is asking the membership question, you can stop as soon as you add the S here and just say yes. If the answer is fill in this table for this problem, then you want it to be complete in that top box, just to be able to answer that. To give you insight into the process of how I would write exams for questions like this, just a couple quick points. We have 50 minutes. If I make a problem remotely this size, we saw how long it took me to derive it. It would have to be about half the exam, I would figure, for your process. If I have more than about 2 or 3 things to cover, that would mean I either need to make a very toy version of this problem or hate the rest of the content on the exam, or we'd have to have exams every couple of days. I don't want to do any of that. The other point is, you're gonna be implementing this as a project. If I were curious to test you on something on an exam, I would probably prioritize something that has an outcome like this last. I would try to find questions for everything else that there's not another outcome that tests before writing a question like this. So you can, while it's going to be on the study guide, assume that it's either going to be very small or non-existent. Questions? What can I help you understand before I go off to office hours, potentially help you with homework questions? Hopefully this was useful.